I'm Robert Anderson.
I'm Joseph Repetti.
I'm Daniel Triana, and this is our dynamics project presentation.
For our project, we have a thin ring and a disc rolling down a plane. They have the same radius and mass, and the angle theta is located right there. So our goals of the project are to determine the ratios of the velocity and the angular velocity at t equals 5 seconds. And also, when t equals 10 seconds, what is the distance d that separates the two? As you can see here, we have our free body diagrams for our initial linear momentum, linear impulse, and final linear momentum. From these free body diagrams, we can determine some of the forces in the x, some of the forces in the y, and some of the moments about O.
To solve for v in the impulse momentum equations, here are your three equations and three unknowns. You're going to set the first two equal to f, and then set those f's equal to each other, and then you're going to get a. Then you're going to plug in both its respective moments of inertias to get an acceleration for each one. Then you're going to plug both of those into the original equations of force, and then you're going to solve for a new f. Alright, this is the impulse momentum equation for the ring. Here we plugged in our new f in the interval from 0 to 5, set it equal to the other side of mv, and then canceled the m's and got 5 halves g sine theta. Same thing here for the discs. Plugged in 1/3 mg sine theta, got 10/3 g mg theta. Cancel the m's, got 10/3 g sine theta. And for the ratio, it's the ring over the disc. So 5/3 over 10/3 g sine theta each comes out to 3/4.
To find the angular velocities of the ring and the disk, we must first use the impulse momentum theorem. In the impulse momentum theorem, some of the moments equal force of friction times r, which equals I alpha. We then use the integral of force friction times r from 5 to 0, which equals I times omega. We then have the force friction, which equals mg sine theta minus ma, and we plug that into the integral equation. Once we plug that into the integral equation, we then substitute in for a, the equation that Danny found earlier, which is a equals mgr squared sine theta over I plus mr squared. We divide by the inertia to get omega by itself. Once we have omega by itself, we can then find the ring, the angular velocity of the ring, and the angular velocity of the disk. For the angular velocity of the ring, we have the inertia equals mr squared. We plug that in for I, and then we get 5g sine theta minus 5 halves g sine theta over r as the angular velocity. And then the angular velocity for the disk, we sub in the I, which is 1/2 mr squared, to get 10g sine theta minus 20 over 3 g sine theta over r. We then, to find the ratio between the two, we plug in the angular velocity of the ring over the angular velocity of the disk, which then gives us 3/4. By using the equations we found in the first section of the problem, we find the velocity of the ring and the disk from t equals 10 seconds to be 5g sine theta for the ring and 20 over 3 g sine theta for the disk. We then find the accelerations. We use the formula v final squared equals v initial squared plus 2a times delta s. V initial squared equals 0. So we plug in the numbers into the equation, and for the delta s of the ring, we end up with 245 sine theta, and the delta s of the disk, we end up with 327 sine theta. We find the disk is ahead of the ring when t equals 10 seconds, and the distance between them equals 82 sine.